This is Physics, Chapter 13, Section 3, dealing with curved mirrors. Our objectives here for today are to calculate distances and focal lengths using the mirror equation for concave and convex spherical mirrors, draw ray diagrams to find the image distance and magnification for concave and convex spherical mirrors, distinguish between real and virtual images, and describe how parabolic mirrors differ from spherical mirrors. Okay, so let's get started. First of all, we deal with spherical mirrors, and the reason we use these, they're not actually used that commonly in actual practice, but because some of the calculations are a little bit easier with them, we kind of use these as a starting point. A concave spherical mirror is a mirror whose reflecting surface is a portion of the inside of a sphere. So if you can imagine taking a globe and cutting a slice off of the globe, a thin slice, the inside surface of the globe would be a concave sphere. And if you make that a reflecting surface, then you have a concave spherical mirror. Concave mirrors can be used to form real images, and these are images where if you put a screen there, you will actually see something on the screen, as opposed to virtual images that are formed always behind the mirror. And no light actually travels there, so if you put a screen up there, it would not show anything on it. All right, so basically, real images form on the front side of mirrors, virtual images form on the back side of mirrors. So a real image is formed when rays of light actually pass through the point on the image. And as I've been saying here, real images can be projected onto a screen. Here you see an example of an object in front of a spherical mirror. You have two main points on the spherical mirror. One is the center of curvature right here. The other one is the focus, which is right here. The relationship between the two is that the distance from the mirror to the focus is 1/2 the distance from the mirror to the center of curvature. And this is the center of curvature is actually the point where the compass would be placed to draw this curved line. Okay, so this is just part of an arc. Okay, so here you see two rays of light coming from the top of this light bulb, or from the filament. The first one strikes the mirror here. Since this is a radius of the mirror that's perpendicular to the tangent at that point, and so the angle of incidence is the angle between the axis and the incident ray, and then the angle of reflection, this angle here, should be equal to this one by the law of reflection. Okay, so we can draw this ray of light that strikes the mirror right at the center and comes back in this direction, such that the angle of incidence is equal to the angle of reflection. And then again, if we draw a ray of light that passes through the center of curvature, since this is a radius, it hits the mirror perpendicular to itself, and that will bounce back right along itself. Therefore, we can see that the image is formed at this point right here. The base of the light bulb is still on the axis. The filament is away from the axis, and you get the image upside down. So this is inverted. It's smaller than the original, so it's diminished. And since this is actually formed on the front side of the mirror, the same side of the mirror as the object, it is a real image. We have a mirror equation which relates the object distance, the image distance, and the focal length of a spherical mirror. Now, your book uses P and Q for the object and image distances. I don't like to do that because it's, for one thing, it's just hard to remember. So I like to use D sub O for the object distance and D sub I for the image distance. I think those are terms that are much easier to remember. And then, of course, we use F for the focal length of the mirror. The mirror equation looks like this. 1 over f equals 1 over do plus 1 over di. All right, we can also state that in words. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And this mathematically is a little bit, you got to be a little bit careful with that. Doing these inverse properties here, adding them together, can be difficult, although most calculators have a key on them that make this real easy, and that is the x to the minus 1 key. That key makes these problems like this easy to solve, and I'll show you that. We also have an equation for magnification, which relates image height and distance to the object and distance to the image, respectively. We have this: the magnification is equal to hi over ho, which is equal to di over d sub o. All right. The magnification is the amount of, you can think of it as the increase in size. A magnification of 1 when hi and ho are equal means that the object and the image are the same size. If the image is larger than the object, you have a magnification greater than 1. If the image is diminished, if the image is diminished, then the object height will be greater than the image height, and this number will be less than 1. So a magnification of 1 means they're the same size. Magnification less than that means it's diminished. Magnification greater than that means it's magnified. And again, here you see that equation in words.
Ray diagrams are useful for checking values calculated from mirror and magnification equations. When drawing ray diagrams for concave spherical mirrors, draw the diagram to scale and mark the center of curvature, C, and the focal point, F. The focal point is midway between C and the mirror. The first ray is drawn from the object to the mirror, parallel to the principal axis. This ray then reflects through the focal point, F. The second ray is drawn from the object through the focal point. This ray then reflects parallel to the principal axis. The top of the image should appear where rays 1 and 2 cross. These 2 rays are enough to locate the image. You can add a third ray, however, to check. Start at the top of the object and draw a ray through C. It will reflect back directly through C again. The image appears where the lines cross. If the bottom of the object lies on the principal axis, then so will the bottom of the image.
So you can use ray diagrams like that to check values. You can use them for estimating, to see how close calculations are, and they can be useful. However, if they're not done accurately and to scale, they can also be misleading. So be a little bit careful of that. Concave mirrors can produce both real and virtual images. In other words, they can be set up to form the image both in front of the mirror and behind the mirror.
When an object is moved toward a concave spherical mirror, its image changes. For object distances greater than the focal length, the image is real and inverted, or upside down. As the object moves closer to the mirror, the image appears further away. This continues until the object is at the focal point, when the image appears infinitely far away from the mirror. When the object lies between the focal point and the mirror surface, the image forms behind the mirror, just as it does for an ordinary flat mirror. The image is now virtual and upright. The light leaving the mirror appears to originate from here, even though it actually came from here.
All right. Alright, so let's take a look at a sample problem. A concave spherical mirror has a focal length of 10 centimeters. Locate the image of a pencil that is placed upright 30 centimeters from the mirror. Find the magnification of the image. Draw a ray diagram to confirm your answers. Alright, if we look at this, first of all we need to determine the sign and the magnitude of the focal length and the object size. The focal length is positive since the focus is located on the same side of the lens as the object, and that's how you determine that. The object distance is also on the same side of the mirror as the focus, and so it is at a positive 30 centimeter distance. So both F and DO are positive. Now, a ray diagram has been constructed here, and you can see that first of all, we had a 10 centimeter focus. That means from the mirror to the center of curvature is 20 centimeters, and the object was placed at a distance of 30 centimeters from the mirror. This gives us a ray diagram that shows that we should get an image that is diminished, in other words, smaller than the object. It's located somewhere between the focus and the center of curvature, and it is inverted. It's upside down. Okay, and we're going to look for that. By the way, in this diagram here, you see the book's uses of the term P and Q. This is what we call D sub O, and this is D sub I, the object distance and the image distance. Okay, so we want to use the mirror equation to relate the object and image's distance to the focal length, and we do that very simply here with, let me grab my pen here. By writing down our equation, 1 over F equals 1 over D sub O plus 1 over D sub I. That's the formula we will use for that. And then the magnification equation in terms of the object and image distances, and that is M equals DI over DO. All right? So first of all, we'll rearrange the equation, our mirror equation, to isolate the image distance and calculate. Okay, so we have, start over again, 1 over F equals 1 over DO plus 1 over DI. We want to solve for the image distance, so that gives us 1 over DI equals 1 over F minus 1 over DO. That gives us 1 over 10 equals, or I'm sorry, minus 1 over 30. All right, so let's take a look at solving this problem using our calculator. You'll notice we have two reciprocals there, and you do have a reciprocal key. On the TIs, it's x to the minus 1. On some other calculators, it might say 1 over x. There may be some different ways of stating it, but basically x to the minus 1 means 1 over. So if we put these numbers in, the first number we have is 1/10. So we do 10 x to the minus 1 minus 30 x to the minus 1. So that gives us 1/10 minus 1/30, and that's equal to that. However, that's equal to 1 over the image distance. So we need the reciprocal of that. So we just push our x to the minus 1 number, and we get our answer of 15 centimeters. So again, you may want to pause and take a look at these keys and practice that on your own calculator. But that's how you get the answer for these problems. And you can see using that x to the minus 1 key makes it really easy. It's pretty painless. So we get 15 centimeters for the image distance. And if you go back to the ray diagram, that looks about right. It was about halfway between the focus and the center of curvature. Okay, we've gotten a little bit ahead of ourselves because we've already done this, substituted in those values and solved for the object or the image distance. However, we still need to solve for the magnification. So let me get my pen set up here, and we will do that. We have magnification is equal to the image distance over the object distance. And we had calculated our image distance to be 15 centimeters. Our object was at 30 centimeters. And so we get 0.50 as our magnification. And this is, because we're dividing centimeters by centimeters, this is a dimensionless number. Okay, so your magnification is always going to be just a plain number. There's no dimensions on that. But there you have it. So we've used the mirror equation to calculate we can actually calculate focal length, object distance, or image distance if we know the other two. And then you can calculate the magnification also. Okay, we'll just go through this. In evaluating this, it makes sense because of the diagram that we had drawn. We see that the magnification, that the object was smaller than the image, and a magnification of 0.5 means it's half the size. So that all makes sense. Okay, a convex spherical mirror is a mirror whose reflecting surface is on the outside part. Remember, we talked about a globe earlier. If you take a slice of along one edge of a globe and make the inside reflective, that would be a concave mirror. If, on the other hand, you make the outside the reflecting part, that would be a convex spherical mirror. Another good example that we're all familiar with is ornaments that you put on a Christmas tree. These are usually very shiny, very mirror-like, and the outside surface is the reflecting surface. And these always provide an image which is virtual because it's on the back side. It looks like it's behind, and it's always diminished. It's always smaller than the object. These are also the mirrors that you commonly see in stores, the anti-shoplifting mirrors that you see in stores, because they give a very wide view. All right, here you see a ray diagram with this. You have the ray parallel to the principal axis that gets reflected back as though it was coming from the focus. Now, again, the focus on a convex mirror is on the back side of the mirror, not on the front side. So the focus is back here. So this ray is reflected as though it was coming from the focus. The second ray is the ray that would pass through the focus, and that ray gets reflected back parallel to the axis. And you can see that by extending the two reflected rays, this reflected ray, by extending that line back, this reflected ray, extend that line back, where they intersect, that's where the image is formed. You also can draw that third ray, and that is the one that would pass through the center of curvature, which is also behind the mirror. That gets reflected back along itself, and again passes through this point right here, which is where the image is formed. Again, you would only need to draw 2 of those 3 lines. Any 2 of those 3 will work. Okay, we're not going to actually do this problem. We'll go through the solution here. A lot of this is let me just point out a couple things here. The focal length is negative because the focus is behind the mirror. So this becomes negative 8 centimeters. Even though the focal length would, if you read the problem, okay, if you read the problem, it tells us that it has a focal length of 8 centimeters. But you have to realize that in a convex mirror, that's going to be negative, all right? And then we're also told that this image is formed behind the mirror, so the image distance is also going to be negative. Those are important things to pull out of a problem as you're reading it. So negative focal length, negative image distance. And here you see the diagram of this. You have your object out here, curved mirror here, convex mirror, and they've drawn all 3 of the rays parallel to the axis, reflecting back as though it's coming from the focus. The ray which would pass through the focus gets reflected back parallel to the axis, and then the ray that would pass through the center of curvature gets reflected back along itself. And it is the reflected rays, so don't go drawing, for example, on this ray right here, don't draw this line in here. That's only going to confuse you. The extension of this line does go through the focus, but if you start drawing that in, you're going to get so many lines back here, it's going to be confusing. It's only the reflected rays, the rays that are coming off the mirror, that you extend back to find the image.
A convex mirror creates virtual images that are smaller than the objects they represent. You will often find convex mirrors in the side view mirrors of cars. To find the size and location of the image produced by a convex mirror, we will draw a ray diagram. First, we draw the object, the mirror, and the focal point. Ray number 1 begins at the tip of the object. It travels parallel to the principal axis towards the mirror. The ray will reflect backwards and at an angle as though it had originated at the focal point. Ray number 2 begins at the object and travels directly towards the focal point. It then reflects back parallel to the principal axis. Draw dotted lines that extend the path of rays 1 and 2 backwards. The dotted lines are light rays that are reflected from the mirror. At the point where the dotted lines cross, the virtual image appears. It is upright and smaller than the object.
Okay, there is a problem with spherical mirrors, and that is known as spherical aberration. Okay, it happens when you use a large aperture, and that means that you have a mirror that uses a significant portion of the sphere, and then rays that are far away from the principal axis will not actually be reflected back to the focal point. And I'll show you a diagram of that in a minute. But we can fix that by using a parabolic mirror. And this is a mirror that's parabolic in shape rather than spherical. And these reflect every ray right to the focus. And so you get a nice sharp image. With spherical aberration, you get an image that is not real clear. Okay, and here you see that light rays that are close to the principal axis get reflected back through the focus, as these two do. But as you get further away, you see this ray gets reflected back so that it goes just a little bit between the focus and the mirror. And then this one way out here is reflected to a point back here. What this means is if these are all coming from a very distant object, the rays are approximately parallel, but they don't all get focused at the same point, and you get a fuzzy image. A parabolic mirror fixes that problem in that every single ray of light gets reflected right through the focus, and you get a nice sharp image. These are, if you look at this shape, this is actually the shape of, say, for example, the headlight on your car. That works a little bit different in that you don't have parallel rays coming in, but you want parallel rays of light going out. So by putting the lamp right here, the headlight right here, the rays of light coming out are being reflected by the parabolic reflector, and they are all going out. So just turn all these arrows around. They're all going out parallel to each other, and you get a very concentrated beam of light coming out from this point. Now you do also have light rays that are coming out this way. You do also have rays of light that are coming out in this direction that are not being reflected off the parabolic portion of the mirror, and that's why you get that that outer area of your headlights, why it's not all just one beam of parallel light rays. In the center of your beam, though, you should have a very concentrated set of rays.
A reflecting telescope works by gathering light using a concave mirror and then directing that light through the eyepiece. Parallel light rays pass down the barrel of the telescope and are reflected by the parabolic objective mirror at the telescope's base. These rays converge toward the objective mirror's focal point, F, where a real image would normally form. However, a small curved mirror that lies in the path of the light rays reflects the light back toward the center of the objective mirror. The light then passes through a very small hole in the center of the objective mirror and comes to a focus at point A. An eyepiece near point A magnifies the image. It is interesting to note that the small mirror and the hole in the parabolic objective mirror do not block out or mask any part of the image. However, they do reduce its brightness slightly.